So in this session we are going to deal with the different laws of electrical circuit. So when you come to this different laws, the today's session we are going to deal with the Ohm's law, Kirchhoff's law, Kirchhoff's current law, and Kirchhoff's voltage law. Kirchhoff's current law and Kirchhoff's voltage law. So these are the three laws. Today's session we are going to deal in a very detailed manner. So when it comes to the Ohm's law, so that Ohm's law, so that scientist is called George Ohm has developed this Ohm's law in order to analyze the electrical circuit. So that is the scientist George Ohm has developed this Ohm's law in order to analyze our electrical circuit. So what is actually the statement of this particular Ohm's law? The statement of Ohm's law: the current flowing through the current flowing through the through the any electrical circuit is directly proportional to the potential difference to the potential difference across the circuit. So this is the statement has been given for this George Ohms in order to analyze this any electrical circuit. So to understand this statement, so let us consider a simple electrical system here, which is supply some source here, voltage source plus minus. So these are the terminals we have. So A and B terminals we have, and if this current, whenever you are giving supply to this specific network, then the current is flowing in this particular circuit, that is I is the current is flowing through this particular circuit. Then whatever the current, and assume in between the circuit, across this circuit I have a potential difference. Across this circuit have a potential difference. That potential difference is also equal to the applied voltage. You have that the potential difference, and that potential difference is also equal to the applied voltage. Then what is the statement here? So according to this statement, for this circuit, the current flowing through this circuit, I, the current flowing through this circuit I is directly proportional to the potential difference across this circuit. So what is this potential difference here? This is nothing but the voltage V. So I can write I is directly proportional to V. If I remove this proportionality constant, I is equal to, I can write V by R. It can be in amperes. I is the current, so I can write in amperes. Or you can write V is equal to IR. So this is the voltage. Or you can write, if you want, R is equal to V by I. That is the ohms. So these are the how you can define different expressions for this particular circuit by taking that Ohm's law. If you draw the VI characteristics for this Ohm's law, if you draw the VI characteristics for this Ohm's law here, then this is V versus I, V versus I. So here you will get the straight line which is passing through the origin. This is line is called at R. So my R is always a constant. My R is the resistance of any conductor is always constant, and for this, even though my voltage is varies, current is varies, but every instant my resistance is passes through the origin, and this is the property AI characteristics of this Ohm's law. And one more, you can say the statement here, or we can take the another statement: the current flowing through the conductor is directly proportional to the potential difference across the conductor. So this statement also is called valid for your Ohm's law. So if you take this is my conductor, if I'm assuming this is my conductor, and this conductor has some internal resistance in it, R, and if you are giving some potential or voltage or supply to this particular circuit, I need to find what is the potential difference across this particular conductor. The potential difference here, that is also equal to V. I can say that is V. And if you write the statement again, that is I is directly proportional to V, or I can be written as V by R. So this is what the statement has been given for your Ohm's law. Then what is the limitation of Ohm's law? Limitation of Ohm's law. So this Ohm's law is applicable to linear circuits. This Ohm's law is applicable to linear circuits, and it does not applicable to non-linear circuits or non-linear circuits which contains such devices like diodes or GNR diodes and voltage regulator. If this kind of devices are have in the electrical circuit, then those circuits are called non-linear circuits, and for that this Ohm's law is not valid. And you also to remember this Ohm's law is valid at constant temperature. We are assuming that our temperature is constant, for which this Ohm's law is going to be valid. So this is how my Ohm's law is giving the relation between the current, voltage, and the resistance of the any electrical circuit, so that from that parts we can analyze our electrical circuit very easily. So now comes to that next law. It's called the Kirchhoff's law. In the Kirchhoff's law, we're going to see what is this Kirchhoff's current law. Kirchhoff's current law, KCL. Kirchhoff's current law. The statement of this Kirchhoff's law is the current entering at a node. So algebraic sum of currents, the algebraic algebraic sum of the algebraic sum of current entering at a node or junction is equal to the algebraic sum of currents leaving the node. So this is the statement I'm giving here. So at any instant of time, any instant of time. So this is the statement I'm giving here. Or the other statement is the algebraic sum of the currents at a node is 0 at any instant of time. So these are the two statements I'm giving to you. So in order to understand what is these two statements and what is going to be defined here. So in order to understand the statement 1 and the statement 2, I'm going to consider a very simple network here. So this is my simple network I'm considering, very simple network with combination of only R network. So this is my network. Sorry, I'm not going drawing well here. Just excuse me. And this is the voltage, and assume R1, R2, R3, R4, and R5. So this is what the network I'm considering here in order to define my Kirchhoff's current law here. So at any point, if you consider the first statement, the algebraic sum of the current entering at a node. So first you have to identify the nodes for a given network. So where you have the network, what is the node? If the two or more electrical elements are connected or joined, that is called a node. So here I have the three electrical elements have been connected. I'm considering these are the nodes. Okay, this is the node A and node B. I'm considering for understanding purpose. So whenever you are giving a voltage to this particular network, so this is some current is flowing in this direction. So current flowing. So I can write. So this whatever the current is flowing in this direction, I take I1. There is also some current is flowing in these directions. In this direction. So this current I can take I2, some X current. This is I3 current, and whatever the I3 is nothing but here I3, and this is my I4 current, and this is the I5 current. So these are the current directions. It can be assumed according to the source which is given here. So this is what, again all these currents are coming here, again coming back to that your main current here, but coming back to the voltage here. So my statement here is I need to write what is the KCL, current law here. So at any point, at any node, I am considering this is my node here. So this is my node. I'm going to consider A point is my node. At this particular node, the current entering at this particular node, which current is entering here? I1 is entering is equal to the current leaving this node. What are the currents leaving here? I3 plus I2. I2 plus I3. So this is what the KCL, isn't it? So this is satisfying my statement. At any node, At any node, algebraic sum of current entering is equal to the current leaving. So current entering this one is equal to algebraic sum of current leaving. Algebraic sum of current entering and algebraic sum of current leaving. So this is what the I1 is equal to I2 plus I3 is. We are going to write the expression according to KCL. Similarly, if you want to write what is the KCL law for this node, if you want to write the KCL law for this node, again go back to this particular node. What is the current entering? Only one current is entering here, so I3 is equal to the algebraic sum of these two. I can write I4 plus I5. So this is also a KCL, that current law we are applying at node B, and this is the expression we are applying current law at the node A. Then comes to the second statement here. Second statement here, the algebraic sum of the currents at a node is 0. The algebraic sum of the current at a node is 0. So that is what? It is nothing but what? Again, if you take this expression here, this is nothing but I can write I1, just take it out, this expression, then minus I2 minus I3 equal to 0. So this is the statement. I can write the same expression in this manner. So this is the algebraic sum. These are the sum of all this current at this node. At this node equal to 0. So this is the statement of the second statement is satisfying me. So this is how we are going to explain the KCL. Now comes to the what is meant by KVL. KVL, Kirchhoff's voltage law. So this can be stated as here the algebraic sum of the voltages in a loop is zero at any instant of time. At any instant of time. So this is the statement for your KVL. So to understand this, let us consider some different electrical circuits here. So this is my voltage and our resistors are connecting like this. Resistors R1, R2 and R3 is there, and this is the one circuit I'm taking. One more is going to consider in here. So this is plus minus some E. I'm drawing in different representation here. Now this circuit has combination of R is there, L and C also there. Now I'm assuming that, come back to the circuit. So some current is flowing here. I is the current is flowing like this. This is the current direction in this circuit and coming back to your source. So whenever the current is flowing through any network, any resistance, it is going to drop some voltage. It is whenever some current I is flowing through this particular resistance, it is going to drop some voltage here. Assume the voltage is V1. Similarly, whenever this current is flowing through this resistance, assume the voltage drop is V2, and here the voltage drop is V3, and the sign convention also you assume here. I am assuming that this voltage drop is plus and minus, this voltage drop also plus and minus, this voltage drop also plus and minus. So I am assuming this sign convention here. So in order to write what is the Kirchhoff's voltage law, so this is algebraic sum of the voltages in a loop. So this is a loop, right? This is a complete closed path loop. So for this loop I can write this algebraic sum of the voltage. this voltage plus this voltage plus this voltage plus this voltage. I can write the expression. So in order to write this expression, so you have to need to remember the concept here. It is called, uh, suppose, uh, if my convention is plus and minus here. Suppose my convention is plus and minus, something like this is there, and my current direction going like this. My current direction is going like this. In this current direction, my convention, that positive and negative sign, as going something like this. Then what I am going to assume is, if this is the current is, I am taking current I is there. So whenever this current is coming like this, it is going like this. Whenever it is meet to the first terminal, so at this first terminal, so this current is the at instant it is entering the positive terminal, isn't it? It is this current I is entering to the positive terminal, and it is leaving the negative terminal. It is leaving the negative terminal. Suppose you can say it is a voltage source. If it is a voltage source, then this is the current direction is going. So here it is entering, and after this it is negative sign, so it is leaving now. Okay. Now what I am assuming, that whenever my current going like this, if it is entering here, going like this, then in this direction, this is my current direction, then it is entering. At the moment it is entering, which sign is going to meet first? It is going to meet to the negative sign. So for this I can write the voltage as minus V. Suppose similarly, if you take any other element, any kind of element, and if it has plus and minus like this, and my current direction is this, then drop is some VR is there here. Drop is voltage across this resistance is VR. Then whenever this current is going through this resistance R, at the instant which is, whenever it is entering to this particular resistance R, at this instant it is meeting the negative polarity here. So for this I can consider this voltage as minus VR. Similarly, if you have another scenario here, it is my plus and this is minus, this is R. So this is the voltage VR is there, and my current direction is now this one. This is my current direction. Then you have to, this is leaving here, this is entering here. So my current is entering at the positive polarity. So I can write my voltage as plus VR. So this is what the convention you need to follow. We need to follow these conventions in order to write this KVL. Now come back to this circuit here. Now see, so this is my current flowing in this manner or in this direction. If you want to write what is this one here, so at this particular moment my current is entering in the negative polarity, so I can write this is minus V. Now it is coming like this, it is going like this. Again at this particular element my current is again entering at the positive polarity, so I can write plus V1. This is V1 voltage, and come here. So this is the current coming, and it is entering at the R2. It is the positive polarity. So plus V2, and coming here the third element, again here my current is entering at the positive polarity. So plus V3 equal to 0. So this is the statement of your KVL. All the voltages, algebraic sum of the voltages in a closed loop is equal to 0, but here we need to define what is exactly the sign. So this is also can be written as the V J, and J start from 1 to N equal to 0. So this is the expression, the algebraic sum of the currents across the loop is equal to 0. I hope you understood how I am writing negative plus 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 of this kind of network. Now come back to this network. So here I'm assuming that, okay, this is already sign has been given. I'm assuming that, so this is plus and minus, this is minus and plus, and this is plus and minus. These are the sign I'm assuming. These are the convention, and this is the voltage drop here. So this is the voltage drop here, and this is the voltage drop here. So I'm assuming VL, VC, and VR as drops, and this is also nothing but what? This is also voltage. So now this is the current is flowing like this. This is the direction of the current is going in a closed loop. Closed loop. Now, if you want to write what is the KVL statement for this network, what is the KVL statement? So I have to start with this element. I will start with this element. At this element, my current entering at the negative polarity, my current entering at the negative polarity. So I can write minus E and going like this, and my current entering at this element at the positive polarity, I can take this is plus VR, and again come here, my current entering at the negative polarity for this particular inductor, so I can write minus VL, and come here, my current entering at the positive polarity of this capacitor, so I can write positive VC equal to 0. So these are the voltages across all the elements. Minus C is the voltage across this element, and VR is the voltage across this element, and VL is this, and VC is across the capacitor. And I'm writing this expression by taking the Kirchhoff's voltage law statement, which has been given to us. So algebraic sum of the voltages in a closed loop is equal to 0, So this is what how we are going to define the KVL. I hope all of you understood this concept, and with this we'll stop this session for today, and next class we will continue with DC circuits.